Okay, I believe we are live now. Hello everyone, and I hope I am audible too. If some, okay, yeah. So I will start with the problem discussion solution for Codeforces round 915. Like the first problem is a constructive problem. Like problem name is constructive problems. It says Gridlandia has been hit by floods and now has to construct all of its cities. Gridlandia can be described as n cross m matrix. Initially, all of its cities are in economic collapse. The government can choose to build certain cities. Additionally, any collapsed city which has at least one vertically neighboring rebuilt city and at least one horizontally neighboring city can ask for aid from them and become rebuilt without help from the government. More formally, collapsed city positions in I, j can become rebuilt if both of the following conditions are satisfied. At least one of the city in position I plus 1 comma j and I minus 1 comma j is rebuilt. At least one of the cities with position I comma j plus 1 and I comma j minus 1 is rebuilt. If the city is located on the border of the matrix and has only one horizontal or vertical neighboring city, then we only consider that city. Now an illustration is also shown here. Like there are two possible ways cities can be revealed by adjacent one second. And we are asked to find, the government wants to know the minimum number of cities it has to rebuild after some time. All the cities can be rebuilt. So if we look at over here, like what we like, and there are some examples, like if these yellow are the cities which the government rebuilds, then in the next step the other two will also be rebuilt, because if we look at this one, like one neighbor one neighbor in the column and one neighbor in the row has already been built. So if we look at these conditions carefully, what we can see is for a particular city to be automatically rebuilt, at least one city in that row should be rebuilt, and similarly for that to be automatically built, at least one row in the column should be automatically rebuilt. And if this condition is satisfied, then everything would be automatically rebuilt. So what we can see is the minimum number of, like at least if we can somehow initially populate nodes in such a way that if each column has at least one city built by government initially and each row has one city built by government initially, then eventually everything will get automatically rebuilt. And if we can that's a minimum possible answer. Maximum of n comma m should be minimum possible answer. Now we have to find some way, like is it possible to achieve it in maximum n comma m? And my claim is yes, we can do that. For example, let's look at so for example, if initial cities look like this, then what we know is that we need at least 4 cities, one in each column, and we also need at least 3 cities, one in each row. And my claim is, if we, let's say if we build cities like this, then in the next step this city would be automatically rebuilt, this will be automatically rebuilt, this would be automatically rebuilt, this would be automatically rebuilt. And once this happens, in the step after this one, this would be automatically rebuilt, this would be automatically rebuilt, and this would be automatically rebuilt. And once this happens, this would automatically rebuild as well. So this way we can ensure that if we build in this order, if we build initially in this order, then we would be able to do everything, and that's how we get the answer as maximum of n comma y. Like if in the example I showed, m is more, but if the situation is different, we can just mirror it. And like any questions, like if n is equal to 3 and m is equal to 3, like we can just ignore this row, right? This one and this one, and that will ensure that everything gets rebuilt automatically. So any more questions on this one before I move on to the next problem? And looks like contest authors are also in the stream right now. Okay, if in case of no questions, I will move on to the next problem. Okay, looks like contest authors are playing around. Okay, the next problem looks like a graph problem. It says you are given a tree, and then there is a definition of tree as well, a connected acyclic directed graph. And we can perform some types of operations, and in one operation we choose two vertices u and v, and then we compress all the vertices on path from u to v into one vertex. In other words, it says all the vertices on path from u to v will be erased from the tree, and a new vertex m will be created, and every vertex s that has an edge to some vertex on path from u to v will have an edge from w. And it also shows an illustrative example of how to do it. Let's say if we are if we have chosen the path from 5 to 1, 5 4 3 2 1, then everything from 5 4 3 2 1 gets compressed into a one node, which they call it 1 comma 5. 11 is a neighbor of 5, so 11 remains. Like 6 is attached to at least one node on this path, so everything over here remains same. And if we look at 9 10 is also attached to one node, so it remains here, nothing is attached to one. So like, and we are asked to find the minimum number of operations we should perform so that the tree remains with only one vertex. So let's take an example of like let's first look at some easy cases. Like let's start with like the tree has only one nodes. Then how many nodes do we need? The answer is, if we have only one node, then we don't need any operations to make a tree with one node. So the answer, if there is only one node, answer is 0. And let's say the original tree is just a path, like there are only 2 leaf node or something like that. If you have a path like this, then we can just choose 1 and 6 and everything will get compressed into only one node. So if the tree has only one node, then we don't need any operations. If tree is just a path where every node has either 1 or 2 neighbors, then the answer is in one operation we can compress it. Otherwise, we can find the 2 nodes which are at maximum distance from each other. Like the idea is, let's introduce the notion of leaf over here. In a graph, we will call a node as leaf if it has only one neighbor. So for example, if a tree is something like this, then in this case, let's call these are the nodes which have only one neighbor associated with them. Let's call them leaves. And the idea is, in one operation we can just remove 2 leaves from the tree. Like if we pick the node which are at farthest distance from each other, in this case this and this is at farthest distance from each other, and if we compress them, this gets deleted, these all gets compressed into one nodes. And the new tree looks like this is the compressed path. This is one node hanging over here. These 2 are also hanging over here. These 2 are hanging over here. And if you look at it, initially there are 1, 2, 3, 4, 5 leaves. Now we have only 1, 2, 3 leaves. So in one operation we can remove 2 nodes over here. So we can probably keep a for loop as well. Like the idea is if so if we are, let's say, initially if we have initially 10 leaf node, then after one operation we will make it 8, then 6, then 4, then 2, and then 1. While if initially there are 11, then we can do it this way. So based on if n number of leaves are even or odd, we can make two cases and find the number of operations required over here. Okay, there are some questions in the chat as well. Like someone says if we count leaf, and the answer will be leaf plus 1 by 2. And yes, this is correct. Like you might have some issues while counting the leaf, that's why you were getting wrong answer. Yeah, like there is one corner case where the root node is also a leaf. So you might have to take a look at it. And someone is also saying they were trying DP on tree where count minimum leaf when a node is root, then use, like, just ensure that if you are doing a DFS, like the root node doesn't have, like the leaf root node is not a leaf, like you can check with the degree over there. And any questions over here before I move on to the next problem? Like I can share my code like how I did. Like for the first problem, like first problem was printing max of both of them. And for the second problem, like for solving it, we don't really need any DFS or anything. The only important observation we need is like leaf node have degree only 1. So when we are taking edges as an input, we can just maintain a degree in an array and then count the number of nodes which have degree 1 and then print leaf plus 1 by 2. So any questions over here before I proceed to the next one? Like the problem with D is, although the code is short and everything, but like once you introduce graph and everything, once that brings up the complexity. Like to think about the leaf, you will have to solve some graph related problems. So like although like based on the number of aces, the difficulty might be that it's 1200, 1300, but to solve it faster, you will have to solve some more graph problems, higher rated problems first. So any questions on this one? Okay, in the chat, few people are mentioning that like C was easier problem than the regular ones. But yeah, like if you look at my screencast, I went ahead with A, B, E, then probably D, then C, then F, something like that. So I will move on to the next problem now. Larger subsequence. Given is a string of length n, in one operation, you can select the lexicographically largest subsequence of S and cyclically shift it to right. They have also given us a definition of what they mean by lexicographically smaller, larger, and they have also given a definition of what does it mean by a cyclic shift over here. Like we will get that definition later. Let's look at what the problem is asking. Your task is to calculate minimum number of operations it would take for S to become sorted, or report that it never reaches a sorted state. So what we are given is, in one operations we will find the lexicographically largest subsequence of S. We will cyclically shift it to right, and then it's asking like minimum number of operations that would require to make the string sorted. And it also says if it's impossible to make it sorted, then we should print -1 as well. Now we are also given the definition of lexicograph, like two string string is lexicographically smaller than string b if following conditions holds. If a is prefix of b and a is not but a is not equal to b, or the first position where a and b differs, the string s has a letter that appears earlier in alphabet than corresponding letter in b. Like let's look at some examples. So I have written some strings here. Like if we compare a and b, what we are told is like AB would be smaller than ABC. It goes by the definition, like if A is prefix of B but A is not equal to B. Here A and B is the prefix of ABC, but these are not equal. Similarly, if we compare ABD and ADC, like if here we can see that AB is not a prefix of ABC, or neither is ADC a prefix of ABC. So let's find the first index where the positions in A and B differ. So here what we can see is like B and D are at different position. Then the first letter that appears earlier in alphabet corresponding to B. So we know that B appears before D. So AB is lexicographically smaller than ADC. Similarly, if we compare ADC and ZAC, like ADC would be smaller because A comes in alphabet before Z. And if we compare ZAC and ZAC, like both of them are equal, so we can't say one is smaller than the other. And like we are also given a definition of some cyclic shift. Like let's just do cyclic shift on these strings as well. It says by cyclic shifting a string t1, t2, tm to the right, we get string tm, t1 up to tm minus 1. So what if we compare them, what we see is the last character becomes the first character if we are doing cyclic shift by 1. So ABC becomes CAB, AB will become BA, ADC will become CAD, ZAC will become CZA, and yeah. So any questions so far before I proceed? Like so far I was just looking at the question only. If there are no confusion, then I will proceed towards the solution as well. Oh, sorry, like I did not realize that I was not sharing the screen. So I have written some examples. Yeah, I will repeat the statement again. So like the statement introduces two definitions, like lexicographically smaller, like it's a string A is lexicographically smaller than B if following conditions hold. A is prefix of B but A is not equal to B, and in the first position where A and B differ, the string A has a letter that appears earlier in alphabet than B. Like I will take some examples to introduce like what does the author mean by this statement over here. So I have created some examples over here, like example strings ABC, AB, ADC, ZAC, ZAC. Like if we compare ABC and AB, like AB also appears in the initial letters of ABC. AB and AB are same. So here in that case, it by first point, we will say that AB is smaller than ABC. Similarly, if we compare ADC and AB, like the first place where both of them differ are B and E. and because B comes first in the alphabetical order than D, so AB is smaller than ADC. Similarly, if we compare ADC and ZAC, like first place where they differ is A and Z, and because A comes in alphabet before Z, it holds that ADC is less than ZAC. Similarly, ZAC and ZAC are equal, so like one is not smaller than, yeah. Like basically the order in which they appears in dictionary. Yes, Rajiv, you are right. Now we are also given that like there is some cyclic shifting over here, and if you look at the definition, it says T1, T2, Tm is the string. If we cyclic shift it, like Tm becomes the first and then all the letters appear. So if we look at these strings again, like cyclic shifting of ABC means C comes first, so it becomes CAB, and if we cyclic shift again, B comes first, it becomes BCA. Similarly, if we try some other string, like let's look at some other string. Cyclic shifting this string means first G comes to the front, it becomes G A C D F, and then if we do it again, F comes to the first, it becomes F G A C D and so on. So any questions over here? And yes, I believe the authors are trolling me. So any questions so far here, like as understanding like what does the problem statement ask us? And like once you understand this, like let's first try to find the lexicographically largest string in S. And let's take some examples from the problem statement itself. Like let's just take this one example. ZBCA, and like if let's add some more characters to it. If we try to find the lexicographically largest string, for a minute let's assume that I am giving it to you. Z like I will take some better example. So I have taken one example where the string is A, B, B, Z, C, D, E, B, A. And if let's say I am also giving you the lexicographically largest string, which in this case would be Z, E, B, A. And let's see what happens if we cyclic shift it once. Like if we cyclic shift Z, E, B, A, then A comes to the front. So in this case, Z becomes A. A comes to the place of Z, Z comes in the place of E comes in the place of B, and B comes in the place of E. So the original string becomes A, B, B, A, C, D, Z, E, B. And if we try to find a lexicographically largest string again, in this case it will be Z, E, B. And if we do the operation once again, it comes here and the string becomes so what we can notice is once if we do it completely, you will notice is that if you look at the initial string, Like the initial string which is present as the lexicographical would be reversed. In the end, it will look more like A, B, B, A, like A in place of Z. Like basically it will reverse. Like Z, E, B, A would be replaced with A, B, E, Z. And if we notice it at the example, like the first character, last character becomes at the first character and lexicographically largest string changes. And once we observe this, what we can do is we can first find the lexicographically largest string in the string. We revert it and we check does the string become sorted. If the answer is no, then it's impossible to make the string it's impossible to make that string sorted, and we should print -1. And if the string becomes sorted, then what we will notice is like the final lexicographical string, largest string will consist of only the characters which are maximum possible number of times. And we like basically keep doing the operation until the string stops changing. So if I continue my example here, now if I do an operation on Z and E, the string becomes, and now if I do operation one more time, I will always choose Z, and changing Z will not change anything. Like that was my idea. And like, oh, sorry, I don't know why I keep on forgetting like switching the string. So here what I did was like this was my example A B B A B A C D Z E B. If I do operation again on like now here the lexicographic largest is Z E B, and if we do B comes to the first and Z E remains. And now if you do an operation over here again, like E comes before Z and the string becomes this. And in this case the lexicographical largest string is Z. And now if you try to do operations again, nothing changes over here. So like if I summarize my approach so far, what we have seen is like if we find the lexicographical largest string in the original string, then whenever we perform an operation, the last element or probably we can say the smallest element from that string comes in the place of first character, and the lexicographical largest string reduces by size 1. This happens for some number of times, and after some time if we try to do operation again, nothing on the original string changes. And what we should do is we should first check like does the string become sorted if we perform maximum number of times the operation. And then there is a claim that the number of operations required is keep doing them until the string stops changing over there. So any questions? Like I will go to my code as well, but yeah. Let's take some example. One second. So like this was my idea as well. Here I am finding the lexicographical largest string and index of all the nodes which are present in the lexicographical largest string, where I am iterating on S, trying to maintain a stack, implicit stack, not an explicit stack, where if the last character is less than current character, keep removing it and keep popping the index, otherwise add this to the lexicographical largest, and so on. Like this makes me realize that I haven't discussed how do you find the lexicographically largest string of S. So yeah, I will also discuss that one. And once you have found the lexicographically largest, what I did was just reverse the lexicographical largest string and then check if it becomes the sorted string. If it does not become a sorted string, answer is -1. Otherwise, the answer is the length of lexicographically largest minus number of times the largest character appears over here. Like let's take some examples too. I have taken this as an example string. Yeah, to find the lexicographic largest string, what we do is we start iterating from this side. First, we maintain an empty string. Then, when we go to 1, we add 1 to A to it. Then we go to B, we try to add B. But what we can notice is if we remove this A, then the string becomes this. And only B is larger than A and B. Now, when we go next, what either we have a choice to make it B or Z or Z. And what we see is only Z is larger than BZ. So we should remove the character B. Now when we try to add character X, what we see is either X, or if we replace it with X, ZX is larger. So we shouldn't remove Z. Now when we go to C, our string becomes ZCX. Now when we go to D, what we notice is if we remove C and replace it with D, the string would be larger. Now when we go to E, what we realize is that if we remove D and if we replace it with E, the string becomes larger. And now when we have A, like removing it with A does not change anything. So, and here, although in my example I have removed only one character at a time, but if let's say this was the string, then it would have been ZX, C, C, then for D we would remove 2 characters. So the idea was find the lexicographically largest string, and let's say our lexicographically largest string is like, let's say this is our lexicographically largest string. After first operation, what we have seen is lexicographically largest string becomes this, and after that operation the string becomes ZZ. And here if we do any more operations, the string does not change. So the idea was find the number of characters in the lexicographically largest string which are not equal to the largest character. So in this case, like the length is 5 minus the number of times the largest character, which is Z in this case. So subtract 3 from here. So after you do operation 2 times, like any more times of operation will not change our string over there. And like essentially that's what I was doing. Like although I did reverse Z multiple times, but the idea was find the length of Z and find the number of times the largest character appears. Print it. So any questions before I move on to the next problem? Okay, I will probably switch my Zoom meeting once Zoom stops. So let's read the problem D. Like its problem's name is cyclic max. For a given array A, define its cost as sum of max of AI something. Some definitions are there. And you are also given a permutation. Definition of permutation is also given. Definition of max is also given. We will look at it. Also at 0 to n minus 1. Find the maximum cost across all cyclic shifts of P. So like let's look at what this max is first. Like it says max of a array is the smallest non-negative integer says x such that x does not appear in B1 to m. So if we look at it, if we like if we have an array like this, the smallest non-negative integer, like basically something greater than 0 or 2 which does not appear in this is 2. So the max of this array would be 2. And let's say if we have this 42001136, the smallest integer which does not appear, non-negative integer which does not appear in this is 5. So the max of this array is 5. Now we are also given the like cyclic shift. Like we are also given definition of permutation. A permutation of set is an array consists of n distinct integers from 0 to n minus 1 in arbitrary order. And there are some examples like 1, 2, 0, 4, 3 is a permutation, but 0, 1, 1 is not a permutation because 1 appears 2 times in the array. At the same time, 0, 2, 3 is not a permutation because for n equal to 3, 3 is, there is 3 in the array. So like, now let's look at a brute force solution. Like how do we do it? Like a brute force n square algorithm would be like, for we find, like we try all the, there are n possible cyclic shifts over here. We try all the possible cyclic shift and we try to find the max of all of them. Like, any confusion on the problem statement first before I move to the solution? Okay, so no confusion on the problem statement. So like, one critical observation in this problem was like, can we simplify this max operation? And the idea is like, because we are given that A is a permutation, what we can do is like, let's say, one second, let me take some example only. I am taking one of the sample example. For the complete array, we know that the max would be n because everything below n would appear in it. If we haven't selected a complete array, let's say this, then what we see is the max of this array is 0. And if we look at the minimum of the remaining part, it's 0 as well. Similarly, if we take this as a subarray, like what we will notice is that max of this part is 4. And if you look at the other part, the minimum in the other part is 4 as well. So the idea is, instead of finding the max of A1 to AI, let's find the minimum of the rest of the part. Like, this was the important observation for this problem statement. Once we know that, then there are more layers for solving it. Like what I did was, like, there is, I tried to maintain a monotonic state of the, okay, one second. Okay, Zoom kicked me out. Give me a minute. I will switch my Zoom meeting. Okay, why do I explain it on Zoom calls? Like, so what I notice is, like, Zoom whiteboard offers a feature known as Lives on Me. So it gives me flexibility to write it on my tablet and save the screen on my computer. So like, once we notice it, like what we can see is, like, we can try to maintain suffix. Like, let's take our original example only. So like, we know that for the complete array, the max would be n. And for all the other of part, let's try to find the minimum suffix min over here. Like the suffix mean over here would be 5. One second. So we can try to sum it up, like what we can compress this array as well. It can be compressed to 0, 5, 1, 1, 4, 1, and 5, 1. Basically the number of times. And let's see what happens when we cyclic shift and moves to the last, 2 to the last. Once we move 2 to the last, the new array becomes now the new compressed array becomes 0, 4, like 0 4 times, 1 1 time, 4 1 time, 5 1 time, 2 1 time. Oh, 1 second. This also becomes 2, this also becomes 2. So we can change it to now when we move 3 to the back again, so you can notice a pattern over here. Like every time we move some element from the top, the length of the last element in the compressed array decreases by 1. We can replace it with the new element of 6, 1, and then we can also remove the element which are larger over here and keep increasing. Yes, the number written in orange is the max of prefix, which what we have realized is also equal to minimum in the suffix. Like the numbers over on the first line are like the numbers in the first line are the max, and like the number on the line after this is number of times a particular max appears, which is in compressed form, like 0 3 times, like 0 is 3 times, so I replace the 0, 3, 1, 1, 2, 3. And like once you have this, you can maintain a DQ, like it's in STL library, and when you remove something from the front to last, you can update it, and at each point of time, if you remove something from the array, you can maintain a running sum of the DQ. If you remove something from DQ, subtract it. If you add something to the DQ, add it. And like any questions over here before I move on to my implementation for this problem? So moving to the implementation part, instead of using an XP, like okay, dry run on a simpler test case, sure. Like let me think of some example over here. I have taken this as an example, and the initial observation we had is for the complete array, the max would be n, which is 6 in this case, and for the rest of the part, the max of the prefix would be minimum element in the rest of the suffix. So for example, if we look at this part, the max would be minimum in the rest of the part, that would be 0. If we look at these two, the max would be minimum in the rest of the part, that would be 0. If we look at the first element, the max would be minimum in the rest of the part, which would be 1. If we look at the first 4, the max would be minimum in the rest of the part, which is 4. And if we look at these, the max would be minimum in the rest of the part, which is 5. And let's not look at the case when everything, like this is only valid when for this particular case where we are given that each element occurs only once and is a max. And my idea was, if we have this array, we can also compress it based on how many times a particular element appears. What we notice here is that this max is also an increasing value. So if I try to compress 0, 0, 1, 4, 5, it becomes 0 2 times, 1 time, 4 1 time, 5 1 time. Like for the running sum part, I will deep dive into my code as well. And now once we move this 2 from the front to the back, then the way max changes is, like that was the idea. Like if you look at it, so initially it was 0, 2. Like once we move something from the front to the back, the frequency of the last element change decreased by 1, and like a new array appeared over here. And since we look at, like now we should also, since we are looking at the suffix min, because 2 appeared after it, this 5 will also become, like for the suffix min will become 2, and 4 will also become suffix min as 2. So this will go away, this will go away, and 2, 1 will be 3. In case it was 4, 5, 2, because we added 2 over there, suffix min 5 also changed to 2, 4 also changed to 2. So, and overall 2 appeared 3 times. Like the algorithm now might sound something familiar to known as monotonic stack. And regarding the time complexity also, I'll come back to it once. Like, so apart from time complexity and how to maintain running sum, max and its count, any other questions over here? Okay, now coming to how do we maintain it. Like here, like I added everything 2 times to make it an array of size n where ai is equal to I plus 1. You can also do it the other way around as well. Now I am iterating all of the elements. I am taking the first element. I am like, since I am putting it in the stack, this is the variable I have stack. You should use q over here. Instead of doing something top from front, I am just using some additional index as well. The idea is, like when you put something into this stack, add current value plus 1, and like let's look at the last element in that. If it is greater, then we should remove it and replace it with the current min. So like here I am changing the delta over here, like whatever you are removing from the stack into number of times gets subtracted from the stack, and whatever stack you are adding, basically number of times you are replacing gets added to it, and at last put it. And the next thing is, at last we also remove the very first element from the top, and here the length decreases. Instead of decreasing the length, I just checked it with ai plus 1. The idea was, like instead of removing explicitly doing pop front, I was maintaining an index RINDX, which denotes how many indexes I have already ignored right now. And then once I added at least n elements to it, because my stack maintains a running sum of n element, I was able to take current value plus n, where n denotes the suffix max of all the elements, and at last I am printing. Now why the time complexity is order n? if we look at it, I am running this for loop 2n times. I insert every time only one element. So yeah, right. The stack has 2n elements only. So like this pop can also happen 2n times only. Like you add an element once and you remove it at max once. The way I am doing compression, so like the compression does not change much over here. And that was the reason it was order n. So the main idea is whenever something gets removed from the stack, its size decreases, and every time its size decreases by only once. So any more questions on this one before I move on to the next problem? Like there are people who might have done it without compression, but like I saw in Codeforces comment someone was doing binary search to find the number of times the new minimum should appear instead of doing. Okay, the one question is ID is going up to 2n, so how do I access a ID? Like if you look at it, like initially I read n elements and then I pushed n more elements. So like once we reach this line, we have every element appearing 2 times in the original array of size 2n. And like what does the dbg do? Like if you look at my screencast, dbg for a vector prints all the elements in that vector. And like if it's a set, it prints everything in the set. If it's map, it prints map 2 times. Like you can check my screencast of how exactly I am using dbg to debug something. Okay, I will move on to the next problem now. So next problem name is 1x. Like it had some story about early segmentary, and like it's saying like how do we implement, like why did I put 2 element twice in an array? Just to simplify my implementation, I could have also done aid modulo n. That also works. A segment is a tree where each node represents a segment and has its number. A segment tree of an array n can be built in a recursive manner. Let's say a function build VLR builds segment tree rooted in the node with number v, and it corresponds to segment L, R. Now let's define build VLR. If L and R are equal, then this node V is the leaf, so we stop adding more nodes. Otherwise, we add 2 edges, V to 2L, 2V, and V to 2V plus 1, and let M is L plus R by 2. We also call build 2V L, M and build 2V plus 1 M plus 1, R. So the whole tree is built by calling build 1, N. So like if someone knows segment tree, then they will find that this is how we build the segment tree, and like the problem did not introduce anything special over here. It's the exact same definition, just reiterated to make it more explicit. I will show like how do we build segment tree once. And now it says we consider a segment tree of n elements. We want to find the LC of S, where S is non-empty subset of leaves. So like we will have to also look at what does LCA of a particular subset means. Then it also says there are exactly 2 to the power n minus 1 possible subset. And since this sum can be large, output is something modulo. And LCA is defined as number of least common ancestor of nodes that are in S. And like I hope some yeah, so like I will just take the original examples in the problem statement. Here if we try to build a segment tree for 2 elements, then we first call it with 1, 1, 2. and then we call it recursively for 2 comma 1 comma 1 and like 3 comma 1 comma 2. And if you look at 1 comma 3, like the same thing happens, we call it for the this part and everything over here. And like the examples are given, like if we try to call it for 1 comma 4, like left part goes to 1 comma 2 and right part goes to, okay, there is a typo over here, this should be 3 comma 4, and this becomes 1 comma 1, 2 comma 2, 3 comma 3, 4 comma 4. And let's say we have chosen, like it also gives us LCA of all the nodes. Like LCA means the parent with the maximum height, which is also the parent of 4. So for example, if we try to find LCA of 4 comma 5, the LCA would be 2. Like 1 is also a parent for both of them, but we need the one with maximum height. And if we look at this 6 comma 7, the LCA is 3 over here. And if we look at 4 comma 7, the LCA would be 1 over here. Like any questions on like what does this mean and everything over here? So moving further over here, like what we can just look at the original definition again. Build v comma l comma r calls 2v comma l comma m and build 2v plus 1 comma r m plus 1 comma r. So the idea is, if we replace v by let's say v plus 2, then this would become 2v plus 4 and this will become 2v plus 5. So and instead of l comma r, we can also replace it with 1 comma n over 1 comma r minus l plus 1. Uh, so the main idea is, instead of let's looking at 1, 2, 3, what we can show is, what we can assume is it's a variable x 1 comma n, and we can try to find it as a function of f of x. And like what it turns out is this function will be of from ax plus b. And if we look at build x comma 1 comma n, it calls build 2x comma 1 comma m we can, instead of going from the index m plus 1 to n, we can also call it as index from 1 comma 1 to n minus m. And if build x comma 1 comma n is ax plus b, then build 2x comma 1 comma n would be 2ax plus b, and build 2x plus 1 comma 1 comma n would be 2ax plus a plus b. Like that will give us the answer for the subtrees. what I said about replacing v by v plus 1 is, like if we say the root of the index of the root is x, then everything, like the answer for that subtree would be of form ax plus b. In the original problem we can replace x by 1, but let's say if the problem statement said we build segment tree with instead of build 3 comma 1 comma n, then how do we find the answer for 3 comma 1 comma n instead of 1 comma 1 comma n? And the same definition follows if 3 comma 1 comma n, then its child would be 6 and 7. So if this if index of this node is v and it denotes element from 1 to n, its child are 2v and 1 to m and 2v plus 1 and m minus 1 to m minus 1, we can also call them. So we need the formula for this. We also need formula for this, and we sorry. So the idea is if we call v 1 comma n, then its left tree would be 2v 1 comma m and its right tree would be 2v plus 1 and m plus 1 to n. We can also change it to denote 1 to n minus m, sorry. So the idea is, let's find the formula for this part, let's find the formula for this part, and let's find the number of subsets for which the LCA is v. So using the answer of this and the number of nodes this v is a part of, we would be able to find overall formula for av plus b. And I will jump to my code now. So the idea was if I know build 1 comma n, then build 2x 1 comma n would be 2ax, and build 2x plus 1 comma n would be 2ax plus a plus b. So I am doing the dynamic programming over here. Like if the number of nodes are 0, then the sum of LCAs would be 0 as well. If the number of nodes is 1, then whatever, like I am returning a pair of integers or amint, and the idea is first part denotes that a and the second part denotes that b in our function ax plus b. So if there is only one node, the sum of LCAs would be like a would be 1 and b would be 0, ax plus 0. If x is 5, the sum of LCAs would be 5. If x is 10, the sum of LCAs would be 10. Otherwise, we can find the size of left subtree size and right subtree size. And we can recursively, using recursion, find the formula for left subtree and the right subtree. And here I am finding the number of subtrees which have current root as an LCA. For that, what we need is at least one node from the left subtree and at least one node from the right subtree. Only then their LCA would be the root. Otherwise, the LCA would either, if everything is from the left subtree, LCA would be in left subtree. If everything is from right subtree, LCA would be in right subtree. So finding the resulting formula for that one, like these many times current V would be the LCA. So it becomes RT. Now since we are replacing the left subtree AX plus B by 2V, so the A becomes 2 times and the right form constants over here. And for the right subtree, the node is 2V plus 1. So like AX plus V becomes 2AX plus A plus B. So like 2 times right part comes here and left plus right comes here, and we return overall the part. And in the end, we know that the sine of root is 1. So like we can replace, we call it for n and we replace x by 1. So it becomes a plus b. Like this was the main idea. Like any questions on this one or something that I should repeat? So I will move to problem F now. So 1 second. Looks like Zoom. Sorry about this one. Like I did not realize like Zoom has limit on the number of pages. Like let's move to the problem F now. We are again given a permutation of length n, and we call an index as good if for all y less than x, py less than px holds, and for all y greater than x, it holds that py greater than px. And we call f of p as the number of good indexes in p. So like we are given some definition of a good index, and we call function f of p as number of good indexes in p. Yes, I will try to change mic or something. Like today I tried doing some noise cancellation on OBS, but probably it's not helping me out here. And we perform the following operation. We pick two distinct indexes I and j and swap elements in pi and pj. And we have to find the maximum value of f of p after applying this operation exactly once. Some definition of permutation is also given. So like any questions on this problem statement? Like I will try to show like what does a good index means. Okay, like Zoom comes in. Like I will take one in the example only. Like one of the example was 6, 7, 6. Like this is one of the example ones. So if we look at over here, like what we have been told is, for let's say if this is an index, if you want to see if it's good or not, everything on this part should be less than 3 and everything on this part should be more than 3. which is not the case here. So 3 is not a good index over here. On the other hand, if you look at 6, no, 6 is also not a good index. Like, let's take some more example. If we take this as example, then what we can see is everything on the left side of 4 is less than 4 and everything on the right side of 4 is more than 4. So 4 is a good index. And my first claim is an index I can be good if and only if P of I is equal to I. It's not necessary that if this condition holds, like if I is good then this definitely holds, but if this holds then it's not necessary that I is a good index. It happens because there are I minus 1 elements less than I and everything should be on the right side of I. And n minus I elements are more than I and all of them should be on the right side of I. So ith index must be equal to I. Like, that's the first claim. Like, my second claim is, if we are performing, let's say, swapping x and y, if there is an index I which is on the left side of x, assuming x less than x, then even if you swap x and y, if something is smaller than I on the right side, that count will not change, although its position will change. So we can never make I good by swapping two elements on the right side. Similarly, if there is an index A which is on the right side of both, even if you swap x and y, if one of them is larger than I, then that will remain larger than I, although its position will change. So if we swap two elements x and y, only the elements between them can become good index. Otherwise, if something is already good, that will remain good. But if, yeah, that was the claim. Like, the second claim is, if we are swapping x and y, then that will not change the goodness of all the indexes which are less than x or all the indexes which are greater than y. So now one more claim. For a particular index I, if there are two elements, like let's say it's 3, 7 and 8, if there are two elements which are greater than that element 2 on the left side, then because we will only change one element from this side and one element from this side, we cannot remove both of the larger elements from the left side. So it's impossible to make 3 a good index by doing any operations only once. And similarly, there is a claim, like, because we will only make one swap here and one swap here, it's impossible to move both of them to the right side. This was essentially my third claim. So now everything boils down to, like, we have 3 set of conditions which is necessary when a particular element can be made good. And now I will jump directly to my code. So, like, any questions so far here before I jump on to my code? So here first I am finding the good indexes. Like, first claim was, if I is good then I should be equal to I. or basically the right part, like there shouldn't be element get, like here I am taking the same definition as the original problem. I am finding the number of good indexes which are originally present in the given array. And if everything is good, then what we know is, because we must swap at least two elements, so our answer will decrease by 2 and we can just finish over there. Otherwise, I am finding, for all the rest of the elements, I am finding one element which we must change on the left side, or at max one element which we must change on the right side. Here I am iterating in the increasing order. I am finding all the elements which are greater than I. If there is only one element, I am finding its index. And if there are two elements, I am marking it as -2. It essentially means it's impossible to make ith index code. Similarly, I am running from right to left as well. I am finding all the elements which are, for I index all the elements which are less than I. If there is only one element, I find its index. If there are at least two index, I simply say it's impossible to make this element good. So like we have three possible set of conditions. Now I am iterating over everything. I am finding left index which I should make good, right index which I should make good, and one possible thing can be like ai is not equal to I. In that case, I will also need I for the ith place. So if I have already found that it's impossible to make it good, continue. If it's already good denotes there is no element on the right side which is larger than it, no element on the left side which is larger than it, and parallel elements equal to I. So I already counted it over there. No need to change it again. Otherwise, if ai is equal to I, then what I know is there is one element on the left side which is larger than it, and one element on the right side which is smaller than it. So I'm essentially adding it in the pair of map. Like if I swap L and R, then I know that I will become good. Otherwise, if there is no element larger than it on the right side, then I know that if I swap I and R, then AI would be good. Otherwise, if there is no element, smaller element on the right side, then if I swap L and I, then this will become good. And once I have found, like for each element I found, like can it be made good using only one swap? And if it can be made good using only one swap, then which two indexes must be swapped? And because we have to make operation only one times, I just find it, like now I iterate on the all possible indexes which I have found, their frequency and the count of original elements which were good, and at last I print the maximum one. Like any questions on this one? Otherwise, I believe I am pretty much done with the discussion for this problem. Okay, thank you everyone for joining.